All right. Good afternoon, physics class. All right. Let's get going on this here, John. Teach you something about called an Atwood machine. So, an Atwood machine is basically two masses and a pulley. Something developed by George Atwood 200, almost 40 years ago. And the reason they're interesting and useful is they allow for situations with constant acceleration. And when you get constant acceleration, then you can study the laws of motion. You know, how do things actually move? How does their motion change? So it's a pretty neat thing. So here's a little example. Students given two blocks of unequal mass. Let's say M1 is greater than M2, which you'll see in the diagrams here. String of negligible mass, so you don't have to worry about the string really, other than that it connects things. And they're challenged to create a multitude of Atwood-style machines and rank them according to the acceleration. So the students set up, well, they said, let's do two blocks and a string with no machine. They drape them over a pulley. They drape them over a pulley on a ramp. Notice the big mass is hanging and the little mass is on the ramp. You could drape them over the pulley the other way, little mass hanging, big mass on the ramp. And then you can drape them over the edge of a table, the big mass hanging and the little mass on the table. And let's pause 1 second. All right, now last flat table pulley with the little mass pulling the big mass. Okay, so, you know, these may seem like something new and complicated, but in fact, they're pretty straightforward. So how do you go about this? We'll talk about the long way of the calculations, and then we'll get into the understandings version of it. And the understanding version is actually quite nice. Kind of like when you look at the homework, those multi-block push or pull problems. You know, there really is a nice way to think about these problems. And then there's a chunky way to think about them, which always works, but you're allowed to do the nice way. All right, so let's go on this. You know, if we're looking at this guy right here, so we can make our little free body. Put a little dot. We can do mass 1. This can be number 1. This can be number 2. Okay. Number 1 has FG pulling down. And number 2 also has FG pulling down. And then number 1 has a tension up. And number 2 then should have a tension down. So we're going to do this real formal like. All right, now you guys may already know what's going on here, but let's be formal about it. So the sum of the forces on block 1 is just that FG1 plus T1. And then same deal over here. The sum of the forces on block 2 is just going to be, change the subscripts, block 2 is going to be FG2 plus T2. Now, I like to show you this because if you approach it formally, it always works. All right, now it's time to clean this junk up. So, nowhere in here do we suspect equilibrium. So this is not going to be 0. Let's start substituting. We'll have mass of block 1 times acceleration of block 1 is going to equal to the mass of block 1 times g, just mg, and T1's in the opposite direction, so minus T1. Fine. And if we look at this one, the mass of block 2 times its acceleration is simply, that should be 2, sorry, is simply the mass of block 2 times g. And it actually points in the same direction, so plus what we've called our positive here, down is positive in this picture, T2. Now here's the recognition, and here's the key fact. Key fact is, for all these tension problems, T1 has to equal T2. And further, as a result of this, acceleration 1 has to equal acceleration 2. They're accelerating together. Okay? Now, given these two, let's resubstitute and clean this thing up. So, m1 times the acceleration that both experience equals m1g minus just plain old t now. And then on this side, we're going to have something similar. m2 times the acceleration that both experience now is just going to equal m2g plus the plain old tension that both experience. Now, the easiest thing to do here is, we're going to bring this business back up over here, is solve both of these for tension and set them equal to each other. Well, if you do that, the one on the left, bring the t over to this side so it's positive, and bring the m1a over to the other side. And so what we're left with then is, and I'm going to start writing, hopefully, singular colors here to save us a little time. You'll have m1g minus m1a. That's from this first equation over here. That's going to equal the tension. And we're going to set this one equal to tension, which then allows us to set them equal to each other. So we're basically doing T equals T. So on the right equation, we have M2A minus M2G. Now this may look like a mess, but let's group like terms, and we'll group them by accelerations. So if we bring both G terms on the left and both A terms on the right, you'll have G times, you're going to have to add this M2G, M1 plus M2. And then on the other side, we have M2A, and we're going to add M1A. So A times, oh, lo and behold, M2 plus M1. And what happens now? Well, divide both sides by M1 plus M2. And they cancel. And you get G equals A. The acceleration is the acceleration due to gravity. No surprise! Kind of figured that would happen, right? Well, when you drop things, yes, of course. Now, there's an understanding way to get this, and I like this understanding way to get this. The understanding way to get this is simply the acceleration of the system. You know, I'm not going to keep writing SYS, but maybe I will. The acceleration of the system is simply going to be the net force on the system divided by the mass of the system. And in this case, you know, this really is a quick way to do it. So let's leave the subscripts out for a moment. Acceleration is, what's the net force here? Well, there were two forces pulling down on this. The tensions cancel, so the net force was Fg1 and Fg2. So that's just the weight of block 1 plus the weight of block 2. And you divide by the mass of the system. Well, the mass of the system is just m1 plus m2. Now, clean this up a little bit. Fg1 is just the mass of 1 times g plus the mass of 2 times g, and hopefully you see what happens here, divided by this same m1 plus m2 down here. Pull out that common factor of G in the numerator. And of course, you end up getting G times M1 plus M2 over M1 plus M2. A is G. And the way to think about this is, up here, this is what's doing the pull. And this is, down here, the numerator, the F net is what's pulling. And the denominator, the mass, is in a sense is what's resisting. That's the inertia. Remember that? So it's simple. What's doing the pulling divided by what's doing the resisting of the motion? Done. There's your acceleration of the system. That really is a nice, clean way to think about these problems. And you may say, oh, well, this is a dumb one. This is easy. The others just draw. Okay, let's go to the next one. Let's see what happens. Let's see what happens. Draped on a pulley. Uh-oh. All right. Why don't we try it the understanding way? Well, yeah, let's do it the understanding way because it's so nice. It's so nice. All right, acceleration of the system. Now you got to think a little bit here, and we'll do it the full way too, don't worry. It's going to be the net force on the system over the mass of the system. Okay, that should say sys, the system. Remember, this is what's pulling, and this, the numerator, the F net is what's pulling, and the mass of the system is what's resisting. Okay? So let's look at our situation here. Cool. All right, what's pulling? Well, it's an F net. So if we quick do a free body for each of these, it's a good idea. Do a quick free body because that'll help clarify. I mean, you could probably see it anyway. But let's call this mass 2 over here. And we'll call this mass 1 over here. So mass 2, Fg is pulling this way. And tension is up, some amount. Tension on 2. For mass 1, Fg is bigger, it's a bigger mass. Something like this. And tension is up. Now we know already. Listen, we can go through and make it formal. But we know already. Let me hug these a little closer together to give us more room to work. We know already that tension 1 and tension 2 are going to be the same. We also know that Fg1 is bigger than Fg2. And we also know that this thing is going to accelerate in the direction of mass 1. It makes sense. So let's check this out. I mean, look, the F net is not a tricky thing here. You've got the tensions are going to cancel, so you're left with two different weights. Now, are they going to add or subtract? Well, one of them is pulling one way and the other is pulling the other. So the F net's going to be a subtraction of the two. You really just Fg of mass 1 minus Fg of mass 2. That's going to give you your net force divided by the combination of the masses. M1 plus M2, because you got to move both masses. And this is really nice and easy. I mean, heck, run it at this point, just plug in. This is going to be M1 times G minus M2 times G over, that's a 2, the sum of the masses, M1 plus M2. So, it might look like it's going to cancel, but it isn't. When you do this one, what you're going to do, you pull out the common factor of G, and it's going to be M1 minus M2 over M1 plus M2. I mean, look at that. Isn't that nice? That's nice. And if you just think about it, like we said here, there are two forces acting on this. The tensions cancel. There are two forces acting. One pulling down, kind of, you trying to rotate this thing clockwise, the other trying to rotate it counterclockwise. So they undo each other, which is why it's a subtraction. So the net force is going to be the weight of 1 minus the weight of 2 over the system mass is the two masses. Boom, done. There's the acceleration. That's it. Done. Now, can we go through this whole process like we just did right here? Absolutely, yes. It's the same exact thing. Let me see if I can pull some of this business here and just copy and paste it. That would be nice. All right. Come on down here. All right. So I'll switch the order around. I called 1 and 2 differently this time. Bring this one over here. All right. Formal. Sum of the forces on block 2 is just the weight of 2 plus the tension. Sum of the forces on 1 is just the weight of 1 plus the tension. All right. Once you substitute in, let's see here. We put in our negatives and all that business. Will it come out the same? It'll come out almost the same. We can copy this business up here too. We'll talk it through. Sorry for copying this over. It's so painful to write on a trackpad. Okay. So I got them out of order again. Let me fix them up. And then we'll talk them through. Don't worry. Bring this over here. Oh. Yeah. Do a little bit of cleaning up yet. This little guy. I can bring over the other side. You come here. Let me erase you. No, I don't want that line. Let me erase you, T1. This is a T1 over here. And let's see if this all makes sense. I just copied and pasted. So M2A2, yep, equals M2G. That's good. Plus T2. Those are in opposite directions. So we're going to make this a minus T2. And then M1A1. Now, notice here you got to be careful. Though these two look like FG1 and FG2, let me call them, or FG2 and 1, though they look like they're pointing in the same direction, they are in fact not. Imagine this rope kind of straightened out a little bit. And over here is block 1, and over here is block 2. Notice they are pointing in opposite directions. You got that? Opposite directions. So if we're going to call this direction on this one positive, well, then you have to follow the rope. That means that this is positive. Follows the rope around. That's the positive direction. Fine. There's no rule on that. That's just the way we pick. Then the other way, this way is going to be negative. This way is going to be negative. This way is going to be negative. So you got to follow the rope when you're doing these. There's a positive direction along the rope and a negative direction. It doesn't really matter. Pick what you want. So here, my M2G is in my positive direction, but my T2 is in my negative. And then my M1G, which points down, that is in the negative direction. And my T1, which points up, is in the positive direction. Cool. That's all we needed. Now we're good. And then knowing that the tensions are equal and the accelerations are equal, we can substitute in over here. Maybe I can type this. We can substitute in over here, and we can say, get a good font size. There we go. We can say that M2A, it's a singular acceleration now, equals M2G minus a singular tension. Over here, M1A, singular acceleration, equals negative M1G plus the singular tension. Cool. Now, if we solve each of these for tension, right? You could actually do that right up over here. Not a big deal. I got to shrink the font a little bit again. Solve each of these for tension. This one is going to bring the T over to the other side. So what you're going to have is T on this side, and then you're going to have minus M2A on this side. And this one, we already got a positive T, so why don't we add M1G to both sides. You end up with, oh, good. Cool. So these two are now equal to each other. Tension, tension. And so now we can rewrite this line as, come on over here, M2G minus M2A equals M1A plus M1G. So now group them. Get the accelerations on one side and get the G's on the other. So if we group them, let's put the G's on this side. If we bring them over, we have to subtract this M1G from both sides. So it'll end up being G times M2 minus M1. Get up there. Equals, and to both sides, acceleration M1 plus M2. Okay? And that's it. Solve for acceleration, and you end up with the same thing we just got. G this divided by now, obviously you can look at one thing here and say, wait a minute. R said M1 minus M2 and yours says M2 minus M1. It's not going to matter here because it's the direction we defined as positive. So from what I did over here, clearly I did actually was more reasonable over here. I defined positive as direction it will accelerate, and it will accelerate in the direction of these purple arrows. In this drawing, I defined positive as up. This one's going to come out negative, this one, and that still means down. So it's the same exact thing. Now, need we really go through the full simultaneous equation process? You can if you want, but I'm telling you, just think of it as the pull over the resistance. You're going to need your free body diagram. But once you have that, this is so clean and nice. All right, let's check out this ramp, right? Ramp pulley 1. You need your free body diagram, so let's not mess around with that. Let's put that in there. Let's see. Thickness. Good. So we'll have this be mass 2 and mass 1. And let's put some forces on there. Okay. Now, both of them have weight. So here's the weight of object 2. Let me number these. So this is object 2, and this is object 1. This one has a bigger weight, so let's put a bigger arrow. Now, this one has tension. Call that T1 if we want. This one also has tension, except the tension is pointed the other way. The tension is following the rope. However, the tension must be the same as T1. So I'm going to put it just as long. There's T2. Now, there are other forces here. There's a couple of things. I'll make dashed. Make this a little thinner and dashed. There's the normal force. But I'm putting that dashed simply because it's not going to impact the acceleration of this. The normal force is perpendicular to the acceleration of this. We also have our FG. We have two components. We have an FG perpendicular, and that one I'm also going to essentially ignore it because it is perpendicular to the direction of acceleration. It's not going to matter for our net force. Finally, we have FG parallel. That one is going to matter. That one does align with the acceleration of this problem. So, can you see it here? I'm hoping you can. Can you see that, like, we're going to have to worry about these two forces, and we're going to have to worry about these two forces. But if we just think about it as what's pulling versus what's being pulled, the F net over the total mass, It really makes this easier. So let's check it out this way. So the acceleration of the system, let me go black again. The acceleration of the system just going to be the net. Well, what's the net force here? Well, if this thing's going to accelerate, the big mass is going to pull it around. It's going to accelerate that way. So let's check it out. If it's going to accelerate, then how will this happen? Well, what's pulling this thing in the direction of acceleration? So we're going to be a little smarter this time. We're going to call the direction of acceleration positive. That'll be our positive direction. I switched it up here, but the truth is it doesn't matter. It still works. But let's call the direction of acceleration positive. That's a good habit. All right. So what is pulling with the direction of acceleration? Well, clearly the weight of block 1. So FG1. Is there anything pulling against the direction of acceleration? Well, as it turns out, yes. The parallel component of the weight of block 2 is pulling against the acceleration down the ramp. So subtract it. Fg of block 2, but only the parallel component. Now you can argue, wait a minute, what about the tensions? You don't need them. They cancel. They have to be equal. You can have positive T or negative T1, positive T2. They're going to cancel out. That's why, what's the net pull? So if you really want, put them up here. Put minus T1 plus T2. But I'm cutting straight to the meat and potato here. What's the mass of the system? It's the mass of block 1 plus the mass of block 2. We're done. We're done. All you got to do now is substitute. So Fg1 is simply mass of block 1 times G minus, now this is the parallel component. So this is the mass of block 2 times G, but the parallel component, the one that pulls down the ramp, is the sine theta. So you need your sine theta up there. Over M1 plus M2. That's it. Now, sometimes what they'll do, and probably frequently, they'll pull that common factor of G out. And so when you rewrite this, your final term will be G times the quantity, M1 minus M2 sine theta, divided by M1 plus M2. Yeah, let's copy and paste that. Okay, so again, what's pulling divided by what's being pulled. That's it. So notice, look at, it's kind of similar here, right? Like in this case, in the pulley case, you're pulling the entire weight of the smaller mass. With that in mind, there's your subtraction term. But in the ramp, you're only pulling a component of the smaller mass. So that's why you're only subtracting off M2 sine theta, not the full M2. Which then means, oh, let's start looking here. Let's start looking at these accelerations. I mean, so far on this page, which one has the greatest acceleration? Well, clearly this one. We're talking about like this is, first place right now. Then between these two, which one is the greater acceleration? Well, the ramp is only pulling against a component of M2's weight, whereas the pulley is pulling against the full M2's weight. So right now, this acceleration is in second place, and this acceleration is in third place. Okay, now let's go on the back. That's supposed to be a 3. Let's go on the back. Let's see what our time check is. Okay. I want to jump you to a table problem before we go looking at this ramp over here. Let's look at this flat table pulley. Now, you know what I'm going to say. Easiest thing is just look at the system. The acceleration of the system is simply the net force on the system divided by the mass of the system. And again, in layman's terms, the pull over the fight or the resist. This, by the way, is a theme in many things in this course. When we do electricity, uh, there's an equation for current that follows the same exact theme. You know, it's how most things in this world actually work, even biologically, physiologically. Your muscles work like this. Okay, so let's go. Free body diagram. Notice the free body, that we have not skipped. There's no shortcut to the free body. Do the free body, it's important. Okay, this is mass 2, and this is mass 1, and let's get to doing. All right, so mass 2, you know what? It does have a weight, but hopefully you realize the weight is actually perpendicular to the direction of acceleration. So I'm going to give it a little dashed line. This thing will accelerate in this direction, so we'll call that direction positive. So basically from M2 toward M1, that's going to be our positive direction. All right. There's also a normal force, but that is not aligned with the acceleration. So as it turns out, it's not going to matter. So it's getting the dashed line. There is definitely a tension on block 2. That's causing the acceleration, so we'll make that solid. And then on block 1, it has a weight. The weight is definitely aligned with the acceleration, so let's put that there. And there's definitely a tension in block 1. It should be the same length as T2. By the way, you know, if you notice here, these lengths are not arbitrary. If it's going to accelerate, then the FG should be bigger than the T1. Certainly. All right, so here it is. T1 and T2, you know, are going to cancel. All right, let's go. I mean, let's see. Let's see what happens here. The acceleration of this system. Well, what is the net force pulling here? T1 and T2 cancel. And the only thing left that's pulling this object in the direction of the rope is actually FG. FG from block 1. So we got FG1 divided by the mass of the system, which is just M1 plus M2. And so if you come over here, the acceleration of the system then is the mass of block 1 times G. I should write it the other way around because we're already done. We're already done. I write it in the order that we've been writing. I'll put G over here times the mass of block 1 divided by the combined mass 1 plus 2. That's it, done. And reasonably, this makes sense as well. This saying that the mass, the weight really of the puller, which is only M1, is then having to pull the combination M1 and M2. So how does this acceleration compare? Well, let's go back and look. So here, this is G times M1 over the sum. On the previous page, this was just G, so that's still first place. But here, look, there are subtractions. So this is G M1, but then you're taking away M2, or you're taking away M2 sine theta. You know what that means? These two just got demoted. This one is now 3. This one is now 4. And ahead of both of them is the table. Because really, it is not fighting against the weight of mass 2. Now, sure, could friction be in these problems? Sure, it could. However, most of these you're going to deal with a smooth surface, so you don't have to worry about that too much. All right, there are 2 others on here. The flat table pulley 2, which is now we have the little mass pulling big mass. And of course, that's going to give us the same exact equation as this one. In fact, I would recommend you go ahead and run through it yourself and make sure it works. It's going to give us the same equation as this one, except one difference, and that is it will be the little mass that's pulling. So it would be GM2 over the sum. And this ramp pulley 2 is also a scenario kind of like that, where over here, we had M1, the bigger mass, pulling. But now we have M2, the little mass, pulling. This one is actually a pretty interesting scenario because depending on the masses, this could go in either direction. You know, in order for this one to accelerate in this direction, the pull this way has to be greater than the pull this way, the other way. And as we saw on the previous page, this pull is M2G, this pull is M1G, but sine theta. So that balance point of where M2G equals M1G sine theta, that's the pull clockwise versus the pull counterclockwise. That's an interesting point because if one is greater, then it accelerates in that direction. You know, the other is greater, accelerates in the other direction. So there's your Atwood machines. And truly, you know, don't get excited about these as if there's something magical or mystical about them. There really isn't. All it is F net over n. It's the F net of whatever's pulling divided by the mass of the system. And I'll tell you, if you really want to be thorough up here, like this, you know, you could have said, so FG1 minus FG2, the one direction in this part of the problem I call positive. So you could have plus T2 minus T1. I mean, it's really this one, we're not leaving anything out. That's really the full description. But of course, the tensions have to be the same, so they just cancel. And that's why I was saving time with that. All right.